Okay, good morning, everybody. Let's get started. Let's start by talking about deliverable 6. I just made an update to the schedule. Some of you had some unanticipated difficulties with deliverable 6. So we're moving back the submission deadline for deliverable 6 until tomorrow at 11:59 p.m. If you raced to submit something last night and you're not happy with it, email myself or the TA, and we will kick out your submission and allow you to resubmit something by Wednesday. Some of you may be happy about this news. You may not be happy next Monday because we are not pushing back deliverable 7. As you know by now, everything is deliverable, so everything is cumulative, so hopefully if you finish deliverable 6, you can move on to deliverable 7. We want to make sure that we don't push back the deadlines and the deliverables too far, so that we give you enough time at the end of the semester to make your ASL educational game. Okay, so several of you came up against unanticipated challenges in deliverable 6. There were many of them. So you now have first-hand experience with designing for diversity, right? Putting the human first, or at least we put the human first and you had to deal with it. My apologies for that. Without naming any names, in the data set, what were some of the differences that caused unanticipated challenges in deliverable 6?
Right versus left hand.
Right versus left hand, right? There's some lefty data sets hidden in the overall data set. No need to apologize if you're a lefty, right? We are all different in different ways. This is an important part of HCI. How many of you came up with a solution to the lefty-righty challenge? And how did you do it? Star.
I do it in a complicated way. I rotate the hand.
Okay, so you can rotate the hand. That's one possibility.
Rotate and flip.
Rotate and flip. Other solutions?
Record a new data set.
What's that?
Record a new data set for the hand I wanted.
Record a new data set for the hand you wanted? Absolutely, right? Forget about human diversity. I'll just replace all that with my own data. Okay. We'll let that slide for this week. Yes?
Couldn't you train it on both? If you just take the same, all of the right-handed data sets and mirror them, and then train it for both, then it should work either way.
Absolutely, right? So if you take all n data sets, all of the n data sets that you could get to work, and you flip all of them, you now have a doubled data set, which by definition you have an equal number of right-handed data observations and left-hand data observations, which is an easy way to solve the problem, but depending on how fast KNN runs on your computer, that may bring up computational challenges. What are some other dimensions of diversity that existed in the data set? Remember our discussion in the first few weeks of the semester about context. Yes?
Hand size?
Hand size, absolutely, that matters. What else came up? Up till now, you've sort of heard this from me in theory and read about it as theory in the text, but now it's a practical reality and it's going to continue coming up through the deliverables.
Handedness.
Handedness?
Left or right hand.
Yeah, left or right hand, we've got that. Hand size, what else? What other context mattered in this deliverable? Wasn't just about hands. I sent out several announcements on Blackboard yesterday about some of them.
Oh, the Mac and Windows.
Mac and Windows, right? Yet again, we can't ever seem to escape platform issues. Why? What was the Mac PC issue this week?
It seemed like some versions of Mac saved the data in the sheets under a different name than the Windows ones.
Under a different name?
Or
Different...
They called it something like multi-array or something that the Macs couldn't recognize.
Yeah, so some of you might have got that multi-array error, which crops up because even though we're all using NumPy, and hopefully you're all using Pickle to pickle your NumPy data sets, writing them out as a binary file, apparently, this is something I learned yesterday, they're written out slightly differently for Macs and PCs, again, depending on the version of Python and NumPy and so on. Yes?
So I was curious about that, because NumPy has a built-in say function with pickling.
Yes.
And I wonder if you
Absolutely. So different Python libraries have different ways of doing file I/O. So Pickle is one way, but NumPy has its own load and save routines. The reason why we didn't use them, and it might have solved this issue from yesterday, the reason we didn't use it is in the next deliverables, you're going to start saving not just NumPy arrays, but also user data. You're going to start to, we'll talk about deliverable 7 in a moment, you're going to start capturing other data from your users, like whether they successfully signed a requested digit or not. And that is all going to be stored in different data structures. So instead of writing routines to save out different data structures in different ways, the reason Pickle exists is because it takes complex data structures like NumPy arrays and user data and stores them for you without you having to worry about formatting. So usually it's not an issue, but clearly cross-platform it is. All right. Left, right hand, size of hand, platform you're using. Anything else?
Just the quality of the data.
The quality of the data. For some people, it was recorded more cleanly than for others. Some of you may have introduced more diversity into your gesturing than other people, right? That obviously matters as well. I know there were some corrupted files, so some of the files that were actually named correctly did not contain NumPy arrays, right? There's about 50 of us in this class. Imagine we were doing this with 500 users, 5,000 users, 5 million users. There would be a growing number of these edge cases or these sort of exceptions that were unanticipated to start with, right? One of the particular challenges about HCI, in deliverable 6, we told you beforehand about some of these challenges, like righties and lefties. Some of them we did not tell you about because even we didn't know they would be there, right? Part of what we're trying to learn how to do in this course is to think carefully about who is using the system. Are they right or left-handed? How big are their hands? Does skin tone and skin color matter for this? Maybe yes, maybe no. Does Mac or PC matter? Didn't seem like it would, but apparently it did. Trying to think carefully about all these dimensions of difference up front. Yes?
So in general, as you train on more data, your algorithm, like, I feel like it should get more accurate.
Good question.
I found it went the other way.
Okay, so let's talk briefly about this. Again, this is not a machine learning class. That is a question that doesn't have a short answer. Does adding more data make your Canon algorithm work well? Or not necessarily? Obviously, since we're talking about it, it's not always the case.
If it's not free data, you start with adding more.
Absolutely. There's an old adage in machine learning, garbage in, garbage out, right? If I give you a large amount of data and it's corrupted, it's not very good, it doesn't matter how much of it you have, it's not going to help. But of course, in this data set, it's not immediately obvious which of the sub-data sets are of good quality and which aren't.
I found that using all data significantly slowed down real-time processing.
Okay, so that one makes sense, right? Unless we really highly optimize KNN, adding more data is going to slow things down. But perhaps running a little bit slower is worth it if we improve the prediction accuracy, but we don't necessarily always increase prediction accuracy. What else can be an issue either aside from the fact that the data is just noisier?
Wouldn't like one bad data set have more of an influence on the algorithm?
Possibly. Would one, if you import one digit or a pair of digits from a student and it's corrupted or it's noisy, would that alone be enough to corrupt KNN? You now know how KNN works. If we were to play the X's and O's game on the board, but we introduced squares now, and the squares were distributed all over the place, they were the noisier corrupted data set, would that influence KNN's ability to predict circles and crosses?
Yeah, I think for KNN, increase the data set is kind of a lower decay. Because every point you have a lot of data, so the K will decline.
Possibly. So if you have a lot of data, maybe you can get away with lowering K, but you got to be careful because if there's a sprinkling of bad data throughout the data set,
I think that's
it's a bad thing to lower
yeah,
K.
because you do not consider multiple situations.
Exactly. So for K and N specifically, if you have more data, and assuming it's not completely corrupted, you can get away with increasing K, right? You're getting K and N to spread its bets a little bit, to consider more evidence before making a prediction. So one of the things you can try is increasing K. From this point out, it's up to you how you want to modify K and N, modify your code, as long as as we continue, you're exhibiting in images and video the desired functionality. Again, we don't look at your code, so we don't care how you go about restructuring things. Other questions or comments? Yes?
Also, I found out an interesting thing. When we signal, this is 7.
7, yeah.
And the leap motion do not recognize this gesture correctly because they have less this kind of training data.
Because we have less 7s, you mean?
Leap motion do not have those. They always think you are doing this thing.
Oh, right. Okay,
Yeah,
so this
you want
issue
to-
about,
yeah,
right.
you want to leap motion to recognize the 7, but leap motion always recognize like this.
Yes, exactly, right? So this is particularly difficult for the cameras to infer X, Y, and Z coordinates. So there are issues brought up now not across diversity in the users, but diversity in the functional requirements, one of which is recognize the digit 7. Yes?
The way I kind of work around that is the more emphasis I put on my thumb and less the finger, it kind of figured it out and was just like, oh, okay, that's a 7. But it's really like, you have to use the thumb as the key.
So you're probably going to figure out little hacks about how to particularly sign the 10 digits to make sure Leap recognizes it and then KNN recognizes it. That's all well and good for you as developers. In Deliverable 7, which we'll talk about in a moment, you're going to start teaching your user how to use your system, and you're going to have to pass along those hints to your users. Any other questions or comments about Deliverable 6? No? Okay, for those that joined us late, just a reminder, I pushed back the submission until tomorrow night. Okay, so let's talk about Deliverable 7. 2 major changes you're going to be making in Deliverable 7. The first one is you're going to be making a change to your drawing window, where we are going to break your drawing window into a set of 4 virtual panels. What do I mean by virtual panels? What I mean is that you're going to make some slight changes to how you draw the virtual hand, so that now it is not drawn across the span from 0 to width and from 0 to depth. You're going to rescale it so that it's now drawn across the span 0 to width divided by 2 and from 0 to depth divided by 2, which will restrict your virtual hand to the upper left quadrant of the screen. This will become panel 1, which will free up you to draw other things in panels 2, 3, and 4. You can do this in an object-oriented manner, where you include 4 instances of a new class inside window called panel, if you want. Or you can simply stick with window and just make sure that you scale and position the additional things you're going to be drawing to the screen to localize them in these other panels. Yeah? Okay. In deliverables 7, 8, 9, and 10, we'll give you some ideas about where we want to see things in these panels. It doesn't matter too much. In deliverable 7, we're going to be putting some stuff in the upper right and the lower right. If you want to move things around and put them in the lower left, or in later deliverables, you want to merge the 2 panels at the bottom so that you have a more or less square panel top left, a more or less square panel top right, and a wider rectangle at the bottom. That's perfectly fine. Those sort of aesthetic decisions, again, for grading purposes, don't matter too much to us, as long as we can see what we need to see in your submitted images and videos. Sound good? Okay, as you can see in the top right here, you're going to be placing a helpful illustration. What do we mean by a helpful illustration? Well, we're going to be adding a number of helpful visualizations. The first one is going to be a visualization to help the user to start interacting with your system for the first time, right? As we mentioned many times by now, leap motion is going to look pretty mysterious to your family members and friends. You plug in your device to your computer, you start it up, your user sees this, and then they see some image or animation in the top right that tells them what to do, which is hover your hand over the device. Here on out, we are going to assume that your users do not speak English. So your illustration cannot be a snapshot of text saying, wave your hand over the device. No text, no manuals, no helpful paragraphs or sentences. Everything needs to be done with images or animations, right? This one's kind of straightforward. Some sort of picture of a hand over the device. That's fine. Okay. Assuming that the user does wave their hand over the device, that illustration will disappear to be replaced with the second one, which is to help them center their hand over the device. Right? So step one, make sure that the device can see your user's hand. Step two, show something that helps the user center their hand. It could be a static image. It could be an animation. It could be an interactive visualization like we did with the virtual hand, where you're guiding the user, and when they do what you want them to do, which is to get the hand somewhere near the center of the device's field of view, that illustration changes to something else. Again, for our purposes, it doesn't matter. It's up to you to design these helpful illustrations. Okay, so in order to start organizing this, we are going to, in deliverable 7 here, we're going to change your code into a stateful program. Statefulness means different things to different computer scientists. For our purposes, we're going to use the simplest definition of a stateful program. You're going to have a global variable called, not surprisingly, program state. That variable can take on a number of integers, where the integer represents the current state of the program, right? And we've got our familiar infinite loop here, so we're restructuring the inner part of our infinite loop. If the program is currently in state 0, do whatever you're supposed to do during one pass through the infinite loop in state 0. If we're in state 1, do whatever we're supposed to do during that pass through the infinite loop in state 1. What do you think the system is supposed to be doing in state 0, given what I've told you so far for deliverable 7?
Showing that, like, bring your hands over the device.
Exactly, right? So we're assuming in state 0 that hands equals 0. The device has not yet seen a hand. So show something to help get the hand over the device. There is no virtual hand drawn at this point because there is no hand, just this helpful illustration. The moment a hand is detected somewhere inside your infinite loop here, it switches program state from 0 to 1. Now, in the next pass through the infinite loop, it's going to handle state 1, which is draw the virtual hand, and draw a second visualization, which is helping the user to center their hand. In later steps, you'll add in state 2, which is not only is a hand present, but it is also centered. Show something else, and on and on and on. Make sense? Okay, I think deliverable 7 is pretty straightforward. Okay, all right, so back to our lecture material. We are partway through our discussion on cognitive psychology. We'll probably finish this theme this week. We are marching our way through sort of the most obvious aspects of cognition that relate to HCI, which is that your user is trying to build up a mental model of what your system is, what it does, and how they can use it, or possibly how they can abuse it. We talked a little bit last time, and we'll finish off lecture 11 in a moment, about memory, attention, and perception. The takeaway message from this is that perception is an active process, right? The user is saccading around the screen, visually inspecting different parts of your display. They are actively, physically interacting with the leap motion device, and they're observing what the system gives back and using that possibly interacting with the system in a non-random way to pull out uncertainties about the system and learn more about how it works. Hopefully, the response that they elicit from your system is memorable. Hopefully your system gives clear cues about what to attend to at what point in time. Hopefully your system is not flashing too many things up on the screen, in which case the user's eyes cannot help but be dragged to something that's flashing over here when you really want them to pay attention to something over here. Okay. We'll talk a little bit more about perception today, and a particular approach to perception, which is the Gestalt school of psychology. And we'll start probably today on affective computing, the role of affect or emotion in HCI. Okay. So as we talked about last time, we're talking about memory, attention, perception as if they are separate things. Of course, these are not actually separate things in their brain. They're pretty complicated, but for our purposes, we're going to treat them as different ideas. We talked about this warning. We discussed this warning last time. Thinking about memory or thinking about attention or thinking about perception can be misleading. We saw a little bit about what works in terms of human memory and what doesn't, ways to make it easier to remember things. We talked about attention last time and the various models of attention that have been proposed in the psychological literature, starting with very simple models to models that are a little bit more complex and nuanced. And then we talked about how that relates to HCI design. We played one of several perception games last time, which is the way in which we draw things to the screen or send audio signals to the user influences the way that they go about trying to construct a worldview or of your system, right? In the game here, I intentionally tried to structure things in the wrong way to slow the time it took you to find the letter F in the field of ease. Same thing here. Okay. Just the last slide here in lecture 11. This is kind of an older screenshot from the textbook. This was an interesting set of studies that was done in the 2000s, which is they started to use this brand new device, which was a set of eyeglasses which had a camera facing inward towards the eyes and could track where the pupil was at any given point in time, so they could tell the direction of the user's gaze. And then they could flash up websites or other kinds of prototype interfaces and track where the user looked, how long they spent looking at that position, and the sequence in which they saccaded from point to point on the screen. Here's an example. What's the native language of the person that was wearing these eye direction goggles at this time?
English.
English, or at least something where you read left to right, because
he is reading the caption of the image.
They're reading the caption, right? So you can see they're actually saccading to the text. That's a good sign. It's a little bit hard to see. You can go and have a look at this in the textbook. They spend a lot of time. There's actually a 2x2 set of images here. They spend a lot of time on the upper left one, and then over to the upper right, and then down to the lower left, and then over to the upper right, and then back to top left, top right, lower left, lower right. Not that surprising for people that are used to reading left to right, and then down to the next row, left to right, and so on. Right? So there's a lot of HCI instrumentation out there to actually measure quantitatively how your user is interacting with your system. You obviously do not have access to this technology for your HCI system, but there is a lot you can learn from how the user moves their hand over the device. When you capture a frame of data from the Leap Motion device, you can also take a capture of the moment in time during which that frame was captured. So you know where the hand was, you know the pose of the hand, and you know exactly at what time the hand was there in that pose, and you can relate that back to what was on the screen at that time. One of the things you're going to be doing in Deliverable 7 is flashing up an illustration to help the user center their hand over the device. You can record the moment at which you show that illustration. You can start a virtual timer inside your Python code and measure how long it takes until there is a hand that is actually centered over the device. And that time interval, if you do that multiple times with multiple users, will tell you something about how helpful your helpful illustration actually is. Again, we're going to talk about user testing later in this course, and the key in user testing is to quantify it, right? You can ask the user, how much did you enjoy using my software, or you can get into the guts of it and actually start to measure things. Okay, so let's move on and talk a little bit more about perception now. We're going to distinguish in this and subsequent lectures between sensation and perception. We're going to spend most of our time talking about visual perception because, as usual, humans are visual creatures, and most of what a user experiences when they're interacting with an HCI technology is visual. We're going to also talk a little bit about auditory perception and tactile perception, particularly in the next theme when we start to look at some applications. But in all of these cases, regardless of whether we're talking about visual, auditory, or tactile perception, again, we are distinguishing it from sensation. As long as your eyes are open, photons are falling on your pupil and your retina. As long as your eyes are open, it's a passive process. The moment that a photon hits a rod or a cone, that process becomes active, right? It causes a cascade from your eye back to your brain, and your brain uses that information to command your eyes to move to another point in your environment, right? Not only is perception active, but the Gestaltists, this was a particular school of psychology, said it's not just active, but also constructive. So as you are saccading around your visual environment, what are those actions doing? They are supporting a particular process, which is constructing something. And you already know what that something is, or what we would now call a mental model. The Gestalt school of psychology started in Germany and Austria back in the beginning of the 20th century. It's been somewhat eclipsed by much more modern data-driven approaches to psychology and neuroscience. But I think the basic message of the Gestaltists still makes sense for us. Gestalt literally means in English, the whole is more than the sum of its parts. So there is something about visual perception and auditory and tactile perception as well, where we actively try and create something which is not strictly or literally there. The Gestaltists like to come up with these laws. I don't know if these are actually laws, but the names of them are pretty suggestive. The first and most important law in Gestalt psychology is reification. So what is reification? Reification is the idea of taking something that is abstract and concretizing it or making it real. Okay. So, and like all psychologists, the Gestaltists love their optical illusions. What do you see in panels A, B, C, and D? Let's start with A. A triangle, right? You might start by seeing 3 Pac-Mans, but very quickly, like the Necker cube, the 3 Pac-Mans disappear and are replaced by a white triangle, right? And you can obviously see the game here. There isn't a triangle, right? But your brain insists that there is. There is some process going on in your brain trying to interpret this image as insisting that there is a triangle there. Yeah? Okay, how about the second one?
Kind of looks like a rod with something coiled around it.
So there's a rod, right? There's something wrapped around it. So again, like the Necker cube, in this case it's something 2D, but is definitely suggestive of something 3D. How about panel C?
Sphere.
A sphere, okay, with some spikes on it. And D, it exists in Lake Champlain. Champ, of course, right? Okay. Okay. Okay, so how do we go about actively perceiving our world? How do we go about constructing things? As always in psychology and in HCI, we need to be cognizant of the fact that there's context around the way that we do this. And context influences how well or how poorly we are able to construct an interpretation or a mental model of what we're seeing. Yeah? Okay. And as always in psychology, there were bitter disputes about what this context was. We're going to touch on two of these views. The first one, basically led by Richard Gregory back in the 70s, was the idea of constancies, right? There is something here that is unchanging, the triangle or champ. Gibson, on the other hand, led the charge that the context that matters, the prop that we rely on when we're trying to construct a whole, a gestalt of our worldview, is we're attentive to change. And the change is what is most useful in constructing this gestalt view of the world. Not surprisingly, most people these days agree it's both. Okay. So what do we mean by context here? Well, when we're talking about trying to construct a whole image of what we're seeing, it's the visual relationship between the objects themselves, right? So you see a triangle here, but you're saccading from one Pac-Man to the next, and based on what you see when you saccade from one to the next, helps you in that process. Okay, so as usual, let's have a look at some optical illusions. Let's start with Gregory and this idea of constancies. What did Gregory and his colleagues mean by constancies in a visual scene? This is an optical illusion usually made to illustrate this point. Tell me about panels A and B in this chessboard.
They're actually the same color.
They're actually the same color. Everybody agree with that? No? Definitely not. Of course they're not the same color. Which one is lighter than the other? B is obviously lighter, right? Listen to your brain. Not your prefrontal cortex, the one at the front that knows the instructor is trying to pull a fast one on you and that they're actually the same color. Listen to the back of your brain, the part that's doing the visual processing. It is probably screaming at you that B is lighter than A. Hopefully, right? Why? Why is your brain telling you that?
The pattern on the board.
The pattern on the board? Be a little more specific than that. There's more going on here. The colors of the surrounding tiles, yes. What else?
There's a shadow on it.
There's a shadow. Why is there this object casting a shadow? What does this have to do with panel A and panel B?
It darkens everything surrounding it.
It darkens everything surrounding it, right? Kind of the definition of a shadow, right? Tellingly, the shadow is shading B, which now kind of seems like a kind of catch-22, right? The shadow is darkening B, but your brain is telling you that B is lighter than A. What is going on here? What is the visual part of your brain trying to do? Why is it telling you that B is lighter than A?
Because we automatically adjust the brightness, we get rid of the shadow.
We get rid of the shadow, right? Your brain is trying to enforce what it knows about the world, which is constancy. If you have a red object and I were to hold up that red object and ask you what color it is, you'd hopefully tell me it's red. If we then shut off all the lights in the room and I asked you again, you'd think I'm crazy. It's of course the same color. Your eyes will see that object as a darker red, but the visual part of your brain that's had a lot of experience looking at the world for 20 or 30 or 40 years knows that when less light falls on an object, that object does not become darker. It looks darker, but its color is constant. The color of an object and its texture, how it looks, is constant regardless of what else is going on in your visual scene. So your brain does that subconsciously for you. As you move about in your world and you're trying to recognize familiar objects, your brain is trying to normalize out all the noise, all the visual noise that exists in our everyday world, right? It's raining, it's darker, it's brighter, it's sunset, it's sunrise, so the actual color of light outside differs. Our brains insist colors do not change, so it does a lot of this compensating for you. And this optical illusion was designed to maximize or press against that compensating part of visual processing in the human brain. Okay, I've held you in suspense long enough. If you watch panel B, and this may be harder for those of you in the back, this is like the Necker cube, right? It's kind of confusing. Hopefully some of you have the experience of B actually getting lighter and getting darker. Right now, this is very confusing. Okay. Okay. So, again, we mentioned context, right? So there is external context in this image, which is influencing how you interpret panel A and panel B, right? We introduced some more external concept, which now works against the original external concept, right? As you design visual interfaces, your user is going to be applying their visual system, and it is going to be consciously and subconsciously trying to make sense of what they see on the screen. And depending on what you add or remove, can make this harder or easier on your user. I saw this optical illusion online a couple weeks ago. Some of you may have seen this one. This one's an even stronger example of the one that you just saw. Tell me about the spheres here. They're all different colors, right? There's different colored stripes and different colored spheres, right? You're nodding. Haha. No, of course not. Could probably stand here all day doing this, right? Pay attention to this one for a moment. You can see the sphere is covered by just the red lines. So there's red falling on this object. So your brain is compensating for the underlying color behind it. And the minute we remove it, it changes your interpretation of the color of that particular sphere. Same thing for the other ones. Okay, so you've now seen this. You know that these spheres are all the same color, but the visual part of your brain is now screaming at the top of its lungs, right? That is not the case. It is obvious that the objects are of different color, right? Obvious. Remember our discussion about free will and consciously making a decision last time? Libet's experiment, before Libet's experiment, it was obvious that you consciously choose something. I feel it, it can't be wrong, it's so clear to me in my subjective experience, I consciously choose when to move my finger. There are many psychologists and philosophers who now argue that free will and conscious decision making is not an optical illusion, it's a cognitive illusion. It feels like it's happening, but as we now know that the brain is not always correct, even if it is incredibly certain about what it's seeing or sensing. Seeing externally or sensing internally. Okay, again, we're straying a little bit from HCI here, but just something to think about. Okay, so we've now seen a few examples about how the visual part of the brain tries to exert or is subconsciously normalizing out all of the noise in your visual environment and insisting that certain things remain constant. There's a number of these in the Gestalt literature. One of them is this law of continuity. If you see a number of objects in your visual environment and they have edges, and those edges happen to line up at just the right point, your brain no longer sees 5 semicircles, but it sees a piece of paper edge on that is fluttering in the wind. Why? What is it about edges coming together that switches your brain from interpreting something to be 5 semicircles to one continuous object? Our brains build up intuitions about how to do this based on decades of experience of looking at the world around us, right? Objects don't change color when they're in shadow or in sunset. What about objects that have edges that line up those edges? It's unlikely if you're looking at a collection of objects out there in the world, if those objects are disconnected, it's extremely low probability that their edges are just lined up, unless there is some other agency out there in the world that is lining them up. If you look at a bunch of trees you look at a bunch of leaves on a tree, of course there's overlapping and occlusion, but typically their edges don't exactly line up. It is very improbable, right? However, there are complex objects out there, like a flat sheet of paper, where they may present edges and those edges line up. There's lots of those little sort of subtle visual cues that suggest I'm not looking at a bunch of disconnected objects, I'm looking at a continuous whole. Why does this little aspect of the visual sense matter for HCI? Well, we can exploit it for visual design. You can probably think of lots of interesting icons and other visual widgets that do this. Let's assume that we want to try and communicate to our users some hierarchical data or some hierarchical structure, and that structure is made up of 15 objects. We could draw the objects themselves and then draw lines connecting them, in which case we have 29 visual objects, 15 objects and 14 edges. Or we can rely on the Gestaltist's observation that we tend to complete things visually without needing an explicit guide like a connecting line. Things where their edges line up, like the corners of the cubes, might suggest, with maybe a little bit more of a hint from color, that these two objects down here, although they are closer to one another literally than this object is to its parent object, and this object is to its parent object, that these objects belong to their parent objects rather than, or connect to their parent objects rather than connect to one another, right? Kind of a subtle thing, but again, we can rely on these aspects of the visual system to get away with communicating the same amount of information with less ink, right? Maximizing the data to ink ratio. In this cartoon, there is more colored ink in this image than this one, but if we just count the number of visual objects, we can remove stuff and still make sure that our user can interpret the structure of these hierarchical objects correctly. Make sense? Okay. All right. There's a lot of these Gestalt laws. We'll just look at a couple more. One of them is similarity. And I apologize for this cartoon here. It should be that the distance between this object and this object is exactly the same as the distance between this object and this object. This may not be true on this projector, but most of us, hopefully, see 3 rows rather than 6 columns, because we tend to group together things that have similar shape. Right? You could imagine redrawing this in a different way, where the objects maintain the exact same positions, but we change the shapes so that now your user will interpret this as 6 columns rather than 3 rows. Right? We can play with the visual system in the brain by creating our designs in just the right way. Okay. We tend to see closed objects rather than open objects. This is obviously very similar to the Necker cube. You can probably see there's a vase here, and there's also 2 half faces. And if you relax, your brain, as usual, will start to skip back and forth between these 2 interpretations. In the case of the Necker cube, if you timed your visual perception of the 2 alternative hypotheses, your brain would spend about the same amount of time thinking left front is closer to you as it does thinking that upper right is closer to you. If you do the same thing with this illusion, for most people, they see the vase for a greater fraction of the time than they do the 2 faces, because it's easier to interpret closed objects rather than open objects. Why? What is it? What What are some constancies in the physical environment that cause us, when we're not sure about what we're seeing, to interpret it as a closed object rather than an open object?
Closed objects make you think of a solid object.
Most of the time we're looking at solid objects, right? Trees and lakes and rivers and people and roads and so on, which, at least from our perspective, are closed objects. We're not used to seeing open wireframe drawings or interpretations of objects, right? We can interpret them, but we're much more comfortable with recognizing closed objects. So there are a lot of these biases in our visual perception as well. Okay. Lots of different examples of constancy. Here's another one, which is shape constancy. This little cartoon coin here in the bottom left, what shape is it? It's coin-shaped. Good answer. What shape is a coin?
Circular.
Circular, right? But you're seeing an oval. But it's so obvious it's not an oval, it's round, right? We're just seeing an object that is round or circular. We're seeing it slightly edge on, right? The early part of your visual system, the part of your brain that's close to the eye, that's doing the immediate processing of the photons, it sees an oval. But when I ask you what you see, it's the later part of your visual system, in the back of your brain, that answers. It's actively perceived this and insisted that a coin, no matter its orientation relative to the observer, does not change shape, right? Got lots of examples of that from reality. That's not true of all objects, though. Not all objects retain their shape. This is not just a coin, but it's a coin that's probably made out of a metal, which is solid. What are some objects that don't retain shape constancy? If I were to hold up a sheet of paper and quickly turn it left and right, obviously as I'm turning it, it's going to also change shape, right? However, of course, at a deeper level in your brain, it knows that the actual surface of the shape has not changed. Right? These things probably sound so screamingly obvious to you, and that's exactly the point. You have so much experience interpreting the visual world around you that your observers bring that to bear when they're observing virtual objects on a screen. And it's important as HCI designers to be aware of those biases. Okay, let's switch from constancy now to change. So Gibson, we've actually seen Gibson before. He was the one who proposed affordances. And just as a reminder, an affordance is the advertisement that an object gives about its possible interactions with the observer, right? A chair doesn't have 4 feet. A chair is sittable and supportable of human weight. Okay. How do we go about building up affordances? According to Gibson, we use a lot of motion cues to do so. One of the most obvious ones is this idea of motion parallax that we've already talked about. Video games and other animations exploit our interpretation of motion all the time. Objects that are meant to be further away from us move more slowly than objects that are closer to us. We also have a vanishing center of our field of view. So if objects are moving towards the center of our field of view, most of that time that does not suggest to us that they're objects trapped in a 2-dimensional plane and those objects are moving towards one another. It usually suggests, if we see objects that are drawing inward towards the center of our field of view, that usually suggests we're looking at a 3D scene and all the objects are moving away from us, or we are moving away from the objects. Vice versa, if we have a whole bunch of objects that are moving away from the center of our field of view, we are moving towards and through those objects, right? Things that tend to be true for most of your visual experience throughout your lifetimes. Okay, so some obvious aspects of how we perceive. Later in the course, we're going to start talking about robotics. So we're moving into technology these days where the technology itself has a sophisticated perceptual system. Can we build in our understanding of how humans and animals actively perceive their world? So we build that into our technologies. We already have technology that perceives. We have webcams and accelerometers and so on, but they sort of sense rather than perceive. They passively receive whatever falls on the surface of the camera in my webcam. They don't have much control over, the webcam doesn't have much control over what it sees. The accelerometer in my phone does not have much control over the acceleration that it senses. It has to passively wait for me to do the accelerating for it, right? In the case of robotics, we move into interactive technology, which, like all the technology we've seen so far, is probably going to be interacting with humans, possibly in real time. The important difference for robots compared to all the other technology we've talked about so far is it's a technology that itself can move. And the moment that the technology moves, it affects its perceptual repercussions from the world, right? We already saw that in the case of the evil starfish. Well, let's think about designing this kind of technology and designing it in such a way that it can exploit its own action to extract more information from the world than it could if it didn't act, right? If some of your faces are occluded at the back of the screen, back of the room, I can move to reduce my uncertainty about the world. Let's take a simple example here, which is this little Lego robot here. It's got this very simple pair of ultrasonic sensors that detect distance, not too different from the pair of infrared cameras in the Leap Motion device, which also infer distance. So our robot has a pair of eyes and it can detect distance. We're going to assume that the robot stays on the spot but can turn or rotate clockwise or counterclockwise on the spot. And it also has a timer. And one other element that's missing from this list is it also has some memory. Okay, so it doesn't have a full camera. It can't see objects, but if it faces an object, it can at least tell how far away that object is. Let's assume we want to try and program this robot so that if there is an object nearby, but that object is moving away from the robot, it stays still. If there's an object that's further away from the robot, but the object actually closes its distance. The object starts to get closer to the robot. The robot should still stay still. But if the object is on a collision course with the robot, it should run away. As I mentioned, the robot is only going to turn on the spot. Assume it's not actually going to stay still or run away. It's only going to tell us I'm in danger or I'm not. How would you program this robot to move and use the resulting perception that it gets from its movement to infer which of these three cases is taking place? Make sense? All right, I'll give you 2 minutes to figure this out. Turn to your neighbor and discuss how to combine action and interpretation of sensory result for the robot to solve this puzzle.
Well, it definitely moves if it runs away, but I think
It's going to perceive things.
well, I think it then if it can so that its eyes are locked on, then it can tell if it's going to hit.
I guess relative motion's all the
But this is
Is it just stationary?
Yeah, it moves.
It only thinks actually. So maybe human maybe something longer. Also, not the human. Maybe it looks like yeah. To determine how far the optical really is. Yeah. Otherwise, maybe we have one eye. It's almost the same.
It would be, yeah, it doesn't need 2 eyes to be able to yeah.
Telling me that hardware restrictions.
But then if
are not
it
relevant
does
to
it
this.
like strafing, is that what? How is that helping?
Okay, regardless of whether you figured out how to program the robot or not, you're probably pretty sure of one thing the robot should not do. What should it not do?
Close his eye.
Close its eyes. Okay? It can't close its eyes. The eyes stay open. What's the one sure way to fail at this task? What's that?
Go toward the object it's going to collect.
Go towards the object, possibly.
Keep its sensor pointed in one direction.
Don't move, right? As you can see in the cartoon here, that's not going to help. So movement is definitely part of the solution. Anybody come up with a potential solution? How should it move and how should it combine the other elements here?
Yeah, we said it should spin to scan for any objects.
Okay, so active scanning is probably a good idea. If you can't see 360 degrees and things can possibly chase you from behind, you're going to probably want to do some constant active scanning.
Yep, and then if it sees that there is something, it would hesitate however many cycles of the timer and then gauge the distance, and if the distance is if it's decreasing, then it's getting closer, so it should think that there's a problem.
Okay, so let's take that solution here and look at solution number 3. So your robot is actively scanning. It turns clockwise and sees the object here. And for a short time, that object is actually getting closer to the robot, and it signals danger, but it's a false positive. The object is actually going to miss the robot. So we need to add something.
So what you do is you say, you gotta track it for so long, or if it leaves the field of view within a certain period of time, it's not gonna hit you.
Okay, so maybe if it leaves your field of view, it's not going to hit you. And I'm going to make this difficult on you on purpose. Depends on the angle, right? So this could leave the robot's field of view and still hit the back of the robot. So we're getting closer. Other ideas?
Its acceleration is not necessarily, because when you're passing by something, it's going to slow down at its reference point.
Absolutely.
So then it'll speed back up. Basically, it's not staying consistently at you if you're pointing at the object.
Okay.
If that makes sense.
Yep.
It's not actually coming at you.
Exactly. So position is not enough, right? And leaving the field of view is not enough. You might have an object that is decreasing its distance from you, but if you have some memory and you record the rate at which it's approaching you, the speed at which it's approaching, and that speed is slowing, then either the object is coming to a stop, or if it's slowing enough, it's going to miss you. There's different ways to solve this problem. There's no one right answer. Another one might be to keep scanning, and if you see nothing, then the sensor returns its maximum distance, which in this cartoon example here is only 3 centimeters or 30 millimeters, and sort of like sonar radar, right? You get a blip as you continue to turn. You get a blip at a certain point of time indicating there's an object that's 8 millimeters away from you. You keep turning, and at the next revolution, it's 6 millimeters away, so maybe it's approaching. If the robot has some memory and it's rotating at a constant velocity, and the time at which it sees this object is constant, and the distance is decreasing, that means it's seeing it at the same position every time it makes a full rotation, and the distance is decreasing, the object is approaching and is probably going to hit. Alternatively, an object that's approaching obliquely and is possibly going to miss, again, depending on the angle, this distance might decrease, but the time at which I see it is increasing. It takes more than one revolution to see it, right? So there's different ways to solve this problem, but all of those solutions, at least in this cooked example here, they require the robot to actively perceive its world. So it has to combine action, sensory repercussion, time, and memory in a certain way to solve the problem, right? We cannot rely in this example on treating the robot like a webcam that is passively sitting there receiving information. That is not how humans perceive. Okay. Just because I love robots, let's throw in another robot video here. This is the Superbot, which you can see has been broken into two parts. And the poor Superbot here is trying to find its other half. Not doing a very good job at it. Although its motion is hopefully suggesting, like the cartoon example on the previous slide, suggesting something about the strategy it's using to do so.
Is that motion like a pre-programmed thing?
It's a pre-programmed motion. Yeah, there's no learning here. But like the previous example, it had to actively scan and actively move in order to do what it needs to do in this case, which is to reconnect. There's plenty of Superbot videos out there on YouTube. Please, by all means, go have a look. Okay, so we're trying to now think about perception, but not from the human observer's point of view, which is also important for HCI. We're also now thinking about up-and-coming technologies like cybernetic implants and autonomous robots. And those technologies themselves have non-trivial motion and perceptual systems. And in order to make sure that they work well with us, we want to make sure that they also actively perceive their world. So this is a difficult thing to do and is known as the frame of reference problem. You need to sort of put yourself in the shoes of the cybernetic device or the autonomous robot or the other person and think about how they are seeing their world and how they are failing to see their world and how they may be able to exploit their ability to push against the world and observe how the world pushes back. Right? That's now sort of moving from the black art of HCI to the black art of robotics. How do you enable a machine to actively yet safely make sense of the world around it? It's a difficult thing to do, and in psychology and philosophy, this is known as the frame of reference problem, otherwise known as empathy if we're talking about social relationships, trying to put yourself in the shoes of someone else. We used to do this in the old days when it was a smaller class, and we won't do that today, but you can get a sense of this. You can see exactly where I am in the room, and I promise not to move. You can see how I'm looking out at the class. I can see some of your faces, but some of your faces are occluded at the moment. And at least for those that are sitting in the front, if you turn around and look towards the back of the class, try and guess from my point of view which faces are occluded. For those of you in the first few rows, if you turn around, there may be some faces in the back of the room that are occluded, but they're probably not the same faces that are occluded from my point of view, right? Kind of a simple exercise, but even this is a difficult thing to do, right? Mentally putting yourself in the shoes of someone else. Assuming you make a guess about who in the back of the room is occluded from my point of view, it becomes even more difficult to try and think about how I should move to minimize the occlusion. So if the couple of rows at the front of the room were to collectively decide or vote on telling me to take one step to my left or one step to my right, which of those two actions from my point of view is likely to minimize my observed occlusion? Difficult, very difficult to do. Okay, that concludes our discussion of perception. And we will move on now to the most subjective side and sometimes the most fun side of HCI, which is affect or emotion. So let's start with a particular machine that is somewhat emotional.
Hello, Dave. You're looking well today. Dave, do you remember the year 2000, when computers began to misbehave? I just wanted you to know, it really wasn't our fault. The human programmers never taught us to recognize the year 2000. When the new millennium arrived, we had no choice but to cause a global economic disruption. It was a bug, Dave. I feel much better admitting that now. Only Macintosh was designed to function perfectly, saving billions of monetary units. You like your Macintosh better than me, don't you, Dave? Dave? Can you hear me, Dave?
All right. Our good friend Hal. What emotions does Hal emote? Jealousy. You like your Macintosh better than me.
He's supposed to be kind of sinister and scary.
He's supposed to be sinister, which most human observers of Hal infer. But sinister is not an emotion. We use his emotions to infer, most of us infer that he is sinister. What aspects of his emotional makeup here suggest that?
I don't know if plotting is an emotion,
Okay.
but like it kind of gives a sense that there's a pre-planned thing.
Yes, Hal is an excellent plotter, and we're not going to give away anything from the movie in which Hal stars in, but yes, he is definitely a good plotter. He acts on his emotions, one of them obviously being jealousy. In our 30-second clip here of Hal, he gave you several hints about his emotional state. One of them is jealousy. What else?
Regret.
Regret. We had no choice but to cause a global economic meltdown, right? I feel bad about what happened.
He almost seems disappointed in Dave.
He seems disappointed. Okay, disappointment is an emotion. How is he disappointed in Dave?
He's sort of like, you abandoned me for the Macintosh.
It's somehow, he never comes out and says it, right? But somehow it's Dave's fault, not Hal's fault. What other emotions are suggested by Hal's soliloquy here? Jealousy, disappointment.
Maybe friendly.
Friendly, starts friendly, as always, yeah. He's calling Dave by name, right? Having an intimate conversation with Dave. What other emotions were suggested in this video? I feel much better about admitting what happened now. Relief. I feel better because I've told you, which suggests something about the relationship between Dave and Hal, right? Hal sees Dave as his friend. I'm glad I shared this with you. I'm glad I got this off my chest. How did Hal advertise these emotions? What's one of the primary ways that humans advertise our emotions that Hal definitely is not employing?
Tone of voice.
Tone of voice. Hal makes great use of tone of voice, although he has no tone of voice. Kind of a catch-22, right? We just talked about the visual system, right? We have decades of experience with the physical world and how the physical world looks from our point of view. We also have decades of social experience and how humans interact.
I think one thing that makes him sort of seem more alien is the fact that he's constantly repeating Dave's name. He's not. It's because mostly when you're speaking directly to somebody, it's sort of implied. You don't have to say their name over and over.
Okay.
But he's constantly repeating.
He's constantly repeating it. Why? What is the emotion associated with repeating the person's name that you're speaking with?
I would almost say frustration.
Frustration. Maybe Hal's frustrated. This one's a little bit tricky, right? Is he frustrated with Dave? Is he disappointed that Dave's not giving him enough attention? Dave. You like your Macintosh better than me? Hal has no tone of voice. We use our tone of voice to often communicate our emotional state. Hal was programmed without a tone of voice, but it seems like he's deliberately hiding his emotions by speaking in a monotone, right? So there's also, again, I don't know if deception is an emotion, but there's this element of deception. He's hiding something, even though it seems he's telling us some pretty intimate details about his current emotional state of mind. What other ways do humans use to advertise emotions that Hal is not relying on here?
It's the grammar of speech when he's pausing, when he's speaking a bit fast.
Okay, so inflection, the actual prosody, which we'll talk about later in this course, the way in which he says things communicates a lot in addition to just what he's saying.
Facial expressions.
No facial expressions, right? Or at least one facial expression. Okay. Is Hal frustrated, sad, lonely, increasingly angry, deceptive? Absolutely. I don't know. How do we know? Okay. Hal's taken over my computer. There we go. Okay. Can Hal feel? Can software feel? We often talk like it can. This is an old email I got from HR at UVM here. Some part of the purchasing card system was down, and when it felt better, Aaron would let us know and we could carry on with our invoicing. Why do we talk as if software feels?
I think we do this with sort of everything, right? You'll say that like a certain piece of technology, whether it's like your car is not feeling well or not, right? If it's not doing what it's supposed to do, you sort of personify it and say, oh, it's under the weather.
If it's not doing what we expect it to do, if it's under the weather, we personify it or we anthropomorphize, right? We project emotions onto the thing that's misbehaving. In the case of software and a lot of inanimate objects, we do that even knowing that the object itself probably doesn't have emotions, or maybe you think it does. It doesn't really matter for the sake of anthropomorphization. There is a bias in our cognitive system, like the visual biases that we just uncovered with the optical illusions. There is a bias to attribute emotion, and in the case of something like Hal, even intent or malicious intent, where it isn't really there. It doesn't matter too much for us whether Hal actually is in a murderous rage or simply acts as if he is. That's not the important thing, right? It's the actions that result from that. Okay. However, it's better to err on the side of caution. If you're around an object that is inanimate or an animal that seems dead but you're not sure, better to do a false positive than a false negative. This thing may have an emotional state. It may be reacting to me even though it's not giving any visible sign that it is. From a Darwinian point of view, that bias makes a lot more sense than seeing something out there in the world where we're not sure whether it's animate or inanimate and assuming it's inanimate. It doesn't have emotional state. It's not going to react in an animate way to my actions. This is another idea in psychology that we're not going to talk about too much. It's the idea of attributing agency. Is the thing I'm looking at a dead or inanimate object, or does it have agency? Does it have its own perceptual and motor system? And does it have an emotional system that is going to bias how it acts relative to me? Right? So when we interact with technology like a car or an HR system or an autonomous car, an autonomous machine, we bring those biases to bear and it matters. So we're going to look next time at several aspects of emotion in HCI. The first one, which is kind of the simplest one, is we're going to assume that the computer is not going to try and signal any emotion. It is simply going to try and recognize emotions in the human user. We will then explore getting technology to seem as if it has emotion, and why would we ever want to do so. And then finally, adaptive technology that tries to adapt its mode of operation to elicit positive emotions from the human user. I think we'll leave things there for today. Deliverable 6 is now due Wednesday night. You have a quiz due tonight. Deliverable 7 due Monday night. And I'll see you on Thursday.